Good afternoon, everyone. This video here is going to help you with section 6.2, particularly the centripetal force, centripetal acceleration formula, or worksheet rather, and then the other worksheet, which the title of it slipped my mind at this particular juncture, but you'll see it on where else but Google Classroom. Okay, so I have a series of questions on the board here, and so we're going to go through those. Now, I want you to know that these answers are basically all in a PowerPoint, and I didn't have enough room to write out everything on the board. So again, the answers in my PowerPoint under this week's, the tab for February 10th through the 16th in Google Classroom. You'll see it there. And I said in the directions, you don't have to like submit that assignment. It's just there for your use. So just so that you are aware. So first question I have here is visualize a horse that is a component of a merry-go-round that is rotating at a constant speed. My question is this horse accelerating? You know, why or why not? So the answer here is this horse accelerating? It is accelerating because the direction is constantly changing. And when you have a change in direction, by definition, you have a change in velocity. Since the change in velocity is occurring with respect to time, that is acceleration. Okay? So even though the merry-go-round, the horse that's part of the merry-go-round is traveling at a constant speed, it's still accelerating because there's a constant change in direction with respect to time. All right? Change in direction means change in velocity with respect to time, so there's your acceleration. Uniform circular motion. Uniform, of course, means one. Circular, obviously traveling in a circular pattern. This is described as the movement of an object or particle trajectory at a constant speed around a circle with a fixed radius. Okay, that's uniform circular motion. Centripetal force, a little bit of a wordy definition, which is why, again, it's in PowerPoint for you. This is the name given to the net force required to keep an object of mass m moving at a speed v along a circular path of radius r. Its direction is always towards the center of the circle, and it continually changes as the object moves. All right, and centripetal acceleration is basically the same thing, talking about the movement of an object along a curved path whose direction is always towards the center of the circle. So, what I'm going to show you here is I've got two examples for you utilizing the centripetal force formula. First of all, that formula looks like this. F subscript c equals m times v squared over r. F subscript c is centripetal force. M for mass, v for speed. Remember, v can be speed or velocity. And then r for radius. So what I did was this first example, I went ahead and plugged in the numbers here. What we're talking about here is talking about bobsledding. Typically, they have it in the Winter Olympics. Not really sure what what bobsledding is. Feel free to, when you have a moment, look it up and check it out. It's kind of an interesting sport to watch. So you have the bobsled has two riders. Total mass of everything is 350 kilograms in this example. The speed is 7 meters per second as it rounds the curve, and the radius is 18 meters. So what that means is this. You have a circle, pretend like that's a perfect circle. Here's the center of it. The radius is out here. All right, meets the line there. So you're rounding a curve, and its radius is a total of 18 meters. Now, what we're doing here is multiplying the mass times the speed is always squared, and that's where students run into trouble. They forget to square the speed. All right, so make sure you're aware of that. Square the speed and then divide by the radius. So 17,150 is a product of 350 times 49. 7 squares, of course, 49. Divide this out, you get 952.78 newtons. And that's it. So you have several problems there. You'll have one question where it asks you to compare your answers and relate it to the centripetal force. Be sure you answer that question. You'll see a pattern in your answers as you work through problems 1, 2, and 3. Now, in some problems, like this one here, notice that I provide you with the centripetal force, and you are asked to solve for the radius. So what you have to do there is first multiply 0.45 times 27 squared. So 27 squared is 729. Then I'm going to multiply that by 0.45, and I'm going to get 328.05. I don't know how well you can see that. I'm assuming you can't, so we'll go with the blue marker here. 328.05 over R equals 113. Now, what we want to do here, we can put this over 1 and cross multiply and divide. And then R is going to be, what would that be? 328 divided by 113. Oh yeah, 2.9. 2.9 meters. All right. So as always, you know, if you don't have the Newton, whatever there, it's fine. The goal is to try to get your answer, try to get the correct answer. All right. So anyhow, that's dealing with centripetal force. And again, centripetal force is that force that is applied as an object is rounding a curve. All right, and the radius is, you know, whatever it happens to be. We solved for the radius here and got 2.9. Up here, the radius we provided for you, and it was a total of 952.78 newtons, given the other information in that particular problem. Okay, now, what I want to do here is I'm going to shift over to the other board here, and I'm going to talk to you a little bit about centripetal acceleration. So give me a second here. We're going to move the camera. Hopefully I won't drop anything or anything like that. Okay, if you got a little motion sickness there, I do apologize for that. Okay. Yeah, we're still running. Good. All right, so centripetal acceleration. Centripetal acceleration, again, the movement of an object along a curved path whose direction is always towards the center of the circle. And that's key. If you think about it, when you're rounding a curve like that, the force is always pushing you towards the center of the circle. All right, so centripetal acceleration. Here's this formula, all right? A subscript C equals V squared over R. A sub C is called centripetal acceleration, V is speed, and R is radius. So, you're given some information in the problem, and it says a bobsled track contains a turn whose radius is 24 meters. Find the centripetal acceleration at the turn if the speed is 34 meters per second. All right, so with centripetal force formula that we just did and centripetal acceleration formula that's right here in front of me, you square the speed. Regardless of the number, you square that speed. So 34 squared divided by the radius is 24. So you type in 34, hit your x squared button, or do 34 times 34, whichever. You divide that out, you get 48.17 meters per second squared. All right? Now, we can take this an extra step. See, what we want to do now is figure out the magnitude of the g-force that you experience based on rounding the curve at this magnitude of centripetal acceleration. So, if that sounds complicated, it really isn't, because all you're doing is you're going to divide. You're going to take this answer here, 48.17. So like this is number 1, and like this is number 2. So you're going to take your answer from number 1, plug it in here for number 2, and do 48.17 you're going to divide it by gravity, 9.8 meters per second squared. Then, for formalities purposes here, I'm canceling out the units because they have, I have it both top and bottom, okay? And then what I want to do then is, once I cancel these out, just go ahead and divide. In this case, I get 4.9 Gs, okay? So that's all you're doing. You're taking the answer from number 1 and dividing it by 9.8, and that's number 2. All right, you'll see it on the worksheet. And then 3 and 4 kind of go together, and number 5, you're going to solve for the radius, which it's the same idea as what we did earlier in the video when I was showing you centripetal acceleration. Now, 4.9 Gs, well, what does that mean? Okay, well, the body, human body, I get this question often. It says, hey, how much G-forces can you experience before you, like, black out? Well, we really don't know because we're not built the same at all. All right? To give you an idea, though, fighter pilots can experience up to 8 or 9, and between 8 and 9 G-forces for a few seconds and be okay. Anything beyond that, a couple seconds, you black out. All right? The roller coasters, like Cedar Point, Kings Island, wherever, on some of the biggest and baddest roller coasters out there, you might experience G-forces in the 6 range somewhere, which is still pretty significant because you have all that extra weight basically pushing on your body and it's almost like compressing you. All right, so if you want to read more about G-forces and that, definitely, look that up. Whatever, heck, do your springs or your second semester technical reading on it. I mean, just to give you an idea. So anyhow, centripetal acceleration, square the speed divided by the radius. All right. This, and then in the next problem, take it a step further, divide by 9.8 to get to figure out the magnitude of G-forces. Between the two formulas, centripetal acceleration is a little bit easier because it's just speed divided by the radius. With centripetal force that I showed you earlier in the video, you have the mass of the object to contend with as well, but it's not that much more difficult than dealing with centripetal acceleration. So, as always, anytime you have questions, let me know. Send me an email. I know, or if you want me to come down and work with you one-on-one, either tomorrow or Friday. I'm definitely up for that. I'll be glad to get out and meet some of you and give you a hand. So anyhow, take care of that worksheet and let me know if you have any questions.